everyone, my name is Amitish, and in this video I'm going to teach you how to think like a mathematician and how to rigorously write down a mathematical proof in the context of a fundamental statement that we all know, which is the basis for long division, which is Euclidean algorithm. The Euclidean algorithm states that if a, b are positive integers, so they're at least one, then there are unique integers q and r, which we call the quotient and the remainder, such that b is equal to aq plus r, where the remainder is between 0 and a. It could be 0, but it's not equal to a, it's less than a, and the quotient is some number at least 0. So this is the precise statement, and I'm going to be very precise in this video to talk to you about how to construct a proof. So we're going to go on a journey together. So let's just dive right into it and try to understand what this statement is saying and how we'd go about a proof. So the basic idea is that what we want to do is we want to divide a into b. Okay, so if you think about it, when you write b is aq plus r, we're dividing a into b and getting a remainder. But we want to make it so that the remainder is less than a. Okay, so how are we going to do this? So I'll first talk about the idea, because that's what governs mathematical proofs. Is we first have to think about what is the idea, which even if you feel it's obvious, we need to be very precise when we write down the proof. So the idea is that if we sort of imagine a and b, right? Imagine the number line. Okay, so I'm going to imagine the number line. I'm going to imagine this is 0, this is a, and this is b. Okay, now what happens is if I keep multiplying a by 2, by 3, by 4, so I keep adding a to itself, I'm going to get numbers like 2a, 3a, etc. Okay, and there is going to be a point. Okay, so I want to divide a into b. I want to take the maximum thing I can multiply with a so that it's still less than b. That's kind of the idea here. So I take the maximal thing. Okay, so in this case, let's say for illustrative purposes, let's say this is 4a. Okay, and then 5a is going to surpass b. Now in this situation, you see that because 4a and 5a sandwiches b, this is where you're going to get the remainder when you do the division. So here we're just talking about the idea to try to visualize how we're going to write down the proof. So what we're going to do here is we're going to say, okay, 4a and b. Well, what's going to happen here is that b is going to equal to 4a plus r. And here you imagine that the remainder is going to be something between 0 and a. Right? Because b minus 4a is going to be smaller than 5a minus 4a, right? So this is the idea. So it's sort of like thinking about this intuitively, we understood that this is how the Euclidean algorithm is going to function. Of course, the remainder could also be 0 if a goes evenly into b, which could be a possibility. So in that case, we'd have 4a is exactly b. But what is beautiful about math is that these kinds of statements, we can think about them very uniformly and concisely. So all these possibilities, what if a goes precisely into b, what if there is a remainder, what if it's 4 and 5, all of these cases are encompassed in this general statement. So we want to prove the general statement to handle all the cases. So what's the idea we've gleaned from this is we've gleaned that we want to look at the maximum multiple of a that is less than b. Okay, that's where you have to sort of think, okay, that is what our q is going to be. Because in our proof, we have to think, what's our q going to be? Well, it should be the maximal multiple of a that is less than or equal to b. Okay, so I'm going to actually now start off with the proof and say that is the q, and then we're going to go on and prove the statement. Okay, so let's do that. So here we're going to define, now that we got the idea, we're now going to state the proof. So we're going to start with the proof. So our proof is going to be, we have to show, right? Our statement is saying that there are unique integers q and r. So we have to show they exist and they're unique. The uniqueness will come next. But first of all, why do they exist? Well, what's our q going to be? We are going to say it's the maximum multiple of a that is less than or equal to b. So here's the proof. So the proof is going to be the following, is let q at least 0 be the maximal integer, such that qa is going to be less than or equal to b. Okay, qa is less than or equal to b. That is going to be our choice of q. And then we expect the remainder is going to be less than a. Why is that? So if we visualize the example we had at the beginning, that was when we took the number line, we could use an inequality to establish that. So because q is the maximal integer such that qa is less than or equal to b, what we can do is we can now define what should our remainder be, right? We're trying to construct a q and an r. What should our remainder be? So let r equal to b minus qa. That's going to be the idea. Now, once we've constructed this, we have to show that the properties are satisfied, right? So Q at least 0 is satisfied. So I'm trying to give you very precise reasoning, right? So sometimes, even if it seems obvious to state, we should be really precise just to make sure we've corresponded with our statement. This is a computer checkable proof in some sense. Okay, it's not just something that we're waving around, we're actually being rigorous. So here Q is at least 0, and we're letting R be equal to B minus QA, and we want to show that 0 is less than or equal to R is less than A. Okay, so first off, so I'm going to use red here, since QA is at least less than or equal to B, we know that R is going to be at least 0. Okay, we know 0 is less than or equal to R, because R is B minus QA, right? You have the inequality QA less than or equal to B, so therefore B minus QA is at least 0. And the second thing is, since Q is maximal, so I'm justifying every step. Okay, so since Q is maximal, what do we know about Q plus 1 times A? Okay, if we think about that number line example at the beginning, the 4A and the 5A exceeded B, so that's how we know that the remainder is going to be less than A. So that's what we're trying to do. So since Q is maximal, we know that, I'm just going to write it in 2 steps, QA is less than or equal to B is less than Q plus 1 times A. Okay, that's by the maximality of Q. Q was maximal so that QA was less than or equal to B, so therefore Q plus 1 times A is greater than B. Okay, so far so good. Now we're going to conclude the proof. We know therefore, and I'm going to write this last step, therefore we know that R is less than A. Why? Because R is equal to B minus QA. So in fact, I'm just going to actually just erase this. We can write that R is equal to B minus QA. So therefore, R is equal to B minus QA, right? B is less than Q plus 1 times A. So this is less than Q plus 1 times A minus QA, which is equal to A. So we have concluded that R is at least 0 and R is less than A. So therefore, we have shown the property that we wanted to show. And the last thing we have to actually verify is that we have that equation that B is equal to QA plus R. Okay, so that equation, of course, comes from the definition of R. And finally, we can write down that, I'm just using colors to kind of emphasize things as well, but we can finally write down that therefore B is equal to QA plus B minus QA, right? Literally subtracting and adding QA, and that's going to equal to QA plus R. So therefore the proof is complete. Okay, so that is the proof of the Euclidean algorithm. There's one more thing left. Okay, so I'm going to prove the uniqueness as well. Okay, but I just want to point out, if you sort of wonder, how did I know to do all this? I'm just sort of going back to the idea we started off at the beginning, that we wanted to show that the remainder has this property. We took the maximal Q so that QA was less than or equal to B. And then to get the information about the remainder, we use the fact that Q plus 1 times A exceeds B. Okay, because we want to basically get this inequality on the remainder. Okay, so that's where I came down to looking at this Q plus 1 times A, and that uses the maximality of Q. So everything has been used in the proof. Everything is tied together, right? We chose Q so it's maximal. It has to be. Because if we chose Q to be some random number, then we would not be able to know the remainder is less than A, because it wouldn't necessarily be true. So the maximality of Q is important. And then once you've got the maximality of Q, everything else follows. Okay, so that was the key idea. That was the thing we had to extract. So the process of going from an intuition to a mathematical proof is, the idea, of course, is the main thing. And then you want to kind of rigorously state it and lead to a proof. Okay, so this is intros to kind of mathematical proofs. Now, the last thing I will explain is why the uniqueness statement is true. And this is actually a very important statement. Okay, it may seem like, okay, some kind of statement, but in math, uniqueness is huge. You know, as you get higher and higher in math, you want to prove stuff is unique. And the trick I'm going to show you here is very prevalent in lots of different things in math. So once you see this trick once, you're definitely going to be very grateful for it. If you haven't seen it already, it's going to use it everywhere. Okay, so why are Q and R unique? So this is how we prove the uniqueness. So I'm just going to erase this. So here we have proven existence. Okay, so this is again something in math. There's existence and uniqueness. Okay, so many things in math you can prove those two things, and you prove them separately. So existence, we have proven that there is this Q and R. Why are Q and R unique? So how do we prove that? Suppose there is another choice of Q and R with the same property. Okay, so suppose this is going to be the uniqueness proof. Suppose that B is equal to Q1A. So I'm going to have two different choices of Q and R. Okay, B is equal to Q1A plus R1, where 0 less than or equal to R1 less than A, and 0 less than or equal to Q1. And also suppose B is equal to Q2A plus R2, where again 0 less than or equal to R2 less than A, and 0 less than or equal to Q2. Okay, so there are two choices ways, two possible ways of dividing with the Euclidean algorithm. Now we're going to show they're actually the same. Okay, so how are we going to show Q1 is Q2 and R1 is R2? Well, I mean, the natural thing is maybe we have these two equations, let's subtract one from the other. Okay, we're kind of trying to solve for one of the variables, we want to get rid of the b. So if you know simultaneous equations, of course, that's a trick to kind of eliminate a variable. So let's try to eliminate a variable here. So what I'm going to do is subtract one from the other. So therefore we get 0 is equal to Q1 minus Q2 times A plus R1 minus R2. Now this is interesting. Okay, this is interesting. Why is this interesting? Well, R1 and R2 are numbers between 0 and A. Okay, so R1 minus R2 is also going to be, it could be a negative number, right? It could be a negative number depending on which one is bigger, but it's going to be something small. Okay, so it's not going to be more negative than negative A or more positive than A, right? It's because there are two numbers between 0 and A, and the Q1 minus Q2 is again some number. Okay, so we're going to now say that, but the Q1 minus Q2 times A is divisible by A, right? It's a multiple of A. And the R1 minus R2 is, as I said, it's not too big. It cannot go beyond A, it cannot go less than negative A. So that basically tells us that something is fishy here. Okay, so what we can do is we can write it out on one side. So therefore, I can write this as R1 minus R2. I can put it on the other side, so get a negative sign. So R2 minus R1 is equal to Q1 minus Q2 times A. However, we know that R2 minus R1 is going to be something between negative A and positive A, right? So that's the key property. So I'm going to now erase this, and I'm going to show that, and then we're going to somehow use that. I mean, that's the intuition, and then we're going to use that to show that the Q1 and Q2 are equal and the R1 and R2 are equal. We know that this equation is true. So we know also that since, so I'm going to write this here, since R1 0 less than or equal to R1 less than A, and 0 less than or equal to R2 less than A, therefore R2 minus R1 is between negative A and positive A. Okay, so that's true. So it could be negative, but it cannot be negative A and it cannot be positive A because there are two numbers within a range of A minus 1 of each other. Okay, so you have this inequality. However, now Q1 minus Q2 times A is going to be, either it's going to be a multiple, Q1 minus Q2 could be positive or negative, either it's a big multiple of A or a negative number that is a multiple of A. But in either case, it cannot equal to R2 minus R1 except in one situation. Okay, so there's one situation where they can be equal, and that's of course when R2 minus R1 is equal to 0, and then Q2 minus Q1 is 0. Okay, so therefore, we deduce that R2 minus R1 is equal to 0 is equal to Q1 minus Q2, which therefore means that Q1 is equal to Q2 and R1 is equal to R2. So that is the argument that therefore the Q1 and Q2 and R1 and R2, or the Q1 and R1 and Q2 and R2 were unique, and that concludes the uniqueness statement. So this uniqueness statement, this idea of kind of subtracting, subtracting, this is kind of a homogeneous trick. It happens a lot in math. So I'm not going to talk about that in detail because you'll see it in higher math, but it's a good place to kind of practice this idea of uniqueness. And the Euclidean algorithm is very powerful. So it may seem like an obvious statement once we understand it, but it's a very powerful statement because it implies lots of things. It gives you an algorithm to find the GCD, the greatest common divisor of two numbers. It generalizes to other settings like polynomial long division. You can use the Euclidean algorithm to divide polynomials into each other. So there's lots of settings and lots of situations where it's very useful. So having a rigorous statement and proof that we now know beyond any doubt is true. It's not just in law, but in math we know beyond any doubt this is true. We've rigorously proved it and practiced some proof-based techniques along the way. Thank you so much for watching. I hope you loved that video, and be sure to check out all the content on my channel. I have lots of different videos where I'm introducing math proofs and teaching you how to think like a mathematician. Once you get past that barrier, it becomes really easy. And really, math proofs and execution of ideas. It's like architecture. You're trying to, you plan it out and then you build it. The building's, okay, laborious, but it is often the easier part once you've got the plan done. Okay, so it's just the process of going from the intuition to the proof, but here's a rigorous proof. I try to be very precise about every statement. One last thing is we used also what is called the Archimedean property of the real numbers to say that there was a maximal Q so that QA is less than or equal to B. Okay, so that's something I will talk about in other videos, but some people like to call that the Archimedean property. Thank you so much for watching. I wish you all the best, and I'll see you in the next video.